So yeah, welcome to this introduction to Julia. One note that if you want to follow along what I'm doing, because most of this presentation will be done with examples with code live. So if you want to check out the slides or the resources or the notebooks, you can scan this QR code or go to this link, or just because it's a GitHub repo, you can just clone it. I'll leave a few seconds for people to do that while I mention that for this presentation, I'm assuming that most people already know some programming, so I won't be doing the very basics of Julia syntax, but you'll be seeing a lot of it. So I chose deliberately to focus on the more advanced stuff that might be relevant for HPC computing. So we'll see how it goes. So yeah, to give you a basic outline of this talk, so I have a first section on the very basics of Julia, but really it's more advertisement for why you might be interested to use it. And the next three will be more done in notebooks to show various concepts and aspects that you can do in Julia. So those being multiple dispatch, and these last two are more important for HPC, being able to benchmark your code to tell its performance, and the last one is how to do parallel programming in Julia, which is actually very easy. So I think many people will be interested. But to start off, why should we use new languages, and in particular, why should we try to decide to learn Julia? And at least one of the reasons that the people who created Julia decided to do so is that they felt that they had this two languages problem. That on one hand, in scientific computing, you had the choice between using some very simple languages like R, Python, or Matlab, which are easy to use but not very fast. And the problem with those is that as soon as you need your code to be performant, you basically have to rely on functions that call underneath fast code from languages like C, C#, C, C++, and Fortran. And the problem with those languages is that they're much harder to use because in C you have to handle all the memory yourself. You have to be careful not to shoot yourself in the foot by doing nasty stuff with memory. So these languages, even though they're much faster, they're much harder to use. And for many years, it has been sort of a trade-off between, okay, I want my code to be fast, or I want my code to be easy to write and easy to understand. And usually it started that you had your first code in Python, Matlab, or R, and then you needed at some point to rewrite some of it in a fast language. And the promise of the Julia suggested that it looks like Python, but it's as fast as C. So that's the promise, and we'll see how it delivers on that. Another important issue for not just scientific computing, but computing in general is that so for many years you had this Moore's law that said that the number of transistors on a chip double every 2 years or so. And that's mostly kept true, but one thing that hasn't is another scaling about the speed at which we can run a thread. And that part actually died out. And you can really see after the 2000 that on this trend, you see that the number of transistors on a chip still goes up. So these are data from microprocessors. So you see that the number of transistors still keeps up with Moore's law, but the speed of your processor does not. And around about the year 2000 or 2005, you can see that you see many processors having multiple cores, and with multiple cores, that means you need to use parallel programming to have really speed on your programs. And on the bottom, I have sort of a few languages that may or may not be relevant for scientific computing, but you see the very old ones like Fortran and APL, and then followed by C and C++. And you also see some of the more modern languages like MATLAB, Python, and R. And from the years 2000 and on, you see this sort of new generation of languages like Rust, like Go, like Nim, like Zip, and Julia. And you can really think of this as a new generation of languages that from the get-go take into account the fact that you are running on multiple cores, you need to do parallel programming, and Julia in particular has a lot of really nice properties for supporting parallel programming that does not really happen in C. And one of the problems in C and C++ is that you can do parallel programming, but it's difficult and the language does not help you, on the contrary. So not being satisfied with these two states of affairs, a bunch of people at the MIT decided to create a language that had both the ease of use of Python and the speed of C, and they called it Julia. And they started a bit around 2010 to work on it, but they sort of unveiled it in 2012 in a paper. And to give you a sort of brief history of Julia is not complete because I haven't included this year, but you can see that, okay, it started, the official announcement was in 2012, and okay, then maybe not much happened until 2017, where only at version 0.6, so still quite in its infancy, one project using Julia was able to join the so-called petaflop club. So the petaflop club is the club of programming languages that have been able to run at above 1 petaflop per second. Prior to that, the only languages on that list were C, C++, and Fortran. So it's interesting to see that the next one would be Julia to enter. And so it was a project in astronomy to catalog some astronomical data. And they achieved a performance above 1.5 petaflop using only Julia. So I think this might be of interest to a lot of actual HPC people here, because it's exactly relevant to what you work on. And so in the following years after that, the speed of development has picked up. So we had the version 1.0 in 2018, then followed by a slew of versions, the latest long-term support version being 1.6. And some time ago last year, version 1.8 has released, which has even more improvement in performance. So it's one thing to note that, okay, we had this sort of landmark project in 2017 with version 1.0.6, but since then the language has come a very long way. So I would expect that if you were to try to replicate what Celeste did, you'd have even more performance because of all the things that have been added since then. Okay, you might ask me, okay, why might I still want to use Julia? Well, one argument is that Julia is fast. So I have here an example of benchmarks. You should take those with a grain of salt because they're quite old at this point, and the program is not necessarily super optimized for each languages. And so the reference in here is C. So you have a bunch of different benchmarks, and C is sort of the reference. And so all the rest is the relative performance relative to C. So you can see that, okay, C is is always at 1, but then you have Julia and NuaJIT, which are surprising because JIT languages, they're very close to C, followed by Rust, Go, Fortran. Those you would expect to be very fast. And then in comparison, you have stuff like MATLAB, Octave, R, and Python that are at least an order of magnitude slower. And the points down there are mostly because it's the matrix multiply, so it relies on layback underneath. So of course it would be reasonably fast. So you see that indeed the claim that Julia is as fast as C is not completely stolen. And I would argue that Julia might fare even better right now. And another really important argument is that if you do literally anything with ODEs, so if you're trying to solve ODEs numerically, there is literally no reason to not use Julia, because the Julia, so in Julia we have the differential equations package, which is a massive suite of ODE solvers for any type of problem you might imagine, and it is the state of the art because it's the largest, has the broadest set of features, and is the fastest, even compared to heads, so stuff like from the Hare ODE. I think it's either C++ or Fortran. You can see that the Julia solvers in green are a bit faster. Note that this is for a stiff ODE, Robert, and if you like this link, there are many more examples of such benchmarks, and across the board, Julia is much faster. And in particular, if you compare to stuff like the orange one, which are the solver from MATLAB, you can see that you have at least 1 or 2 order of magnitude of speed compared to that. So this is not trivial. It really means that your code and you solving this much faster. So, and in fact, this whole package is probably responsible for about easily half of the people joining and starting to use Julia because of how good it is. Some last few points. So you might want to use Julia because it's open source. You don't have to pay a MATLAB license. It also means that compared to MATLAB, because you have the Julia community developing open source packages, the development of new features and new packages has been much faster than the proprietary MATLAB developers can keep up. Another point is that it is made for numerical computing. So from the get-go, Julia was intended to be a competitor to MATLAB, be a competitor to R, and as such, it does directly target numerical computing. So you have, by default, a good array library, you have a good linear algebra library, you have all of these functions that you need for numerical computing that you don't necessarily have by default in languages like Python. In Python, you have to use the library NumPy, which is not directly in the library, and that can cause problem. Some other points that are a bit sort of ancillary is that your code in Julia is Unicode, so you can use arbitrary Unicode characters, and it's nice because it means that your code can look like math. And as a scientist trying to translate your equations into code, it's non-trivial. It means that really your code looks exactly like the math on your paper. And also for those in the know, Julia is actually secretly a Lisp, so you can do some meta programming with that, and it's pretty powerful. Now, before you accuse me of being too much of an evangelist, I will give you a few reasons why you might not want to use Julia. So one reason, it's open source, which means that unfortunately the documentation can be not great, especially for packages. And you can also have a lot of projects on packages with only one maintainer. And the problem with that is that if the developer or maintainer just stops working on his project, then the project is effectively dead. And if you wanted to use it, then too bad. You either have to work on it on yourself or try something else. Another recurring problem is that because in the way Julia works is it's a combined language, but it's JIT compiled. And that entails that every time you restart Julia and you restart your Julia program, some parts of your program have to be recompiled. And that means that at startup, you'll always have some delay between the start of your program and your result. And that means that, for example, if you compare the time it takes to show a plot in Julia and Python, Python will be a bit faster. But if you do 1,000 plots, Julia will be faster. Another point is that right now the error messages in Julia are not beginner friendly. So this is sort of a message that if you are sort of a grizzled and experienced developer, you can go through it easily. But as a beginner, if you get a massive message all in red with not much useful information, it's not a great experience. Another point against Julia is that it's a competitor to Python, but it's still tiny. I think there are still less than 10,000 officially registered Julia packages. Compared with like the above 50,000 or maybe hundreds of thousand packages for Python. So it does mean that the Julia ecosystem is much smaller. And a last argument, I have really heard people take this as an argument to not use Julia, is that in Julia, your array indices start at 1, unlike Python or C. But if you're coming for Fortran, you're not bothered by that. So yeah, do be aware the arrays indices start at 1. Okay, by the way, you can interrupt with the questions at any time. It's not supposed to be a lecture, so if you have any questions, feel free to shoot them. If not, I will jump into the actual explanation of some of Julia's mechanics. So one of the most important parts of Julia is that it has a type system. So Of course, every language is a type system, but some languages had it for you. So for example, in Python or in Matlab, you don't really see the types. You have, okay, values, and you know that this is a double, this is a character, but you don't have something that tells you, okay, this is definitely a chain of characters. This is definitely an integer of this size. In Julia, it's the opposite. You do have this information about the types of your variables, although you don't have to show it all the time. And another point is that, so this is an example of the small portion of Julia's type system is that in Julia you have so-called abstract and concrete types. So the distinction that a concrete type like float 64, float 16, float 32, it's really something that gets mapped into memory. So for example, on the bottom, it's the floating point numbers. So float 64 would be the double, for float 32 would be the regular float you have in C. And above that, you can see that they're all linked to some type called abstract float. So this is an abstract type, which means that it does not represent anything in memory, but there's a relation that we say, okay, all of these concrete types are subtypes of abstract float, and abstract float is sort of an abstract type to gather all the floating point number types. And then, of course, abstract float is itself a subtype of real, which is the abstract type for real numbers, which is itself a subtype for number, which is the abstract type for all numbers. So things that you can add, subtract, multiply, and divide. And then above that, you have the any type, which is sort of the type that's match anything. And generally, you want to avoid using any because your performance may be pretty slow. So to give you another description, so the type system in Julia is dynamic, meaning you don't necessarily have to specify the type of your variable every time you define it, but you can optionally give a type annotation. This also means that at runtime, the type of your variables is inferred by the compiler. And an important point is that it's parametric. So for example, I can write a type called vector t, vector being simply a one-dimensional array, and t being some arbitrary type, which I don't care. So this just means a vector of a one-dimensional array of type t. And so this means that you can effectively have generic types, which is a very useful feature that it's hard to get in C or Fortran, for example. And as I showed on the previous slide, you have a subtyping relation, as in object-oriented programming between your types. For example, float 64 is a subtype of real, and all of this is used, in fact, in another feature that I will cover next. So maybe before that, I will give you another description of Julia. So it's anytime you describe a language, a programming language to someone, it's nice to just tell them what are the first-class citizens. So to recall, a first-class citizen programming language is an object that can be returned by a function, passed as an argument to a function, can be assigned to a variable, and that can be, and you can form an expression that returns a value of this object. So for example, in Julia, you can do that with functions. So this means that Julia can do some basic form of functional programming because you can return a function from a function. You can write a function that takes a function as an argument, and you can write lambda expressions to get sort of anonymous functions. Types are also first-class citizens. So you can, if you have type T, the type T, so this expression is the type of type T. So you can also work with directly the types of your variable in your code. And finally, this goes back to my comment about Julia being secretly a Lisp. In Julia expressions themselves are first-class citizens. So you can take a Julia expression and just have it syntactically as just an abstract syntax tree within Julia and manipulate it. And so this allows for some pretty powerful metaprogramming abilities. For example, you can write macros that completely change how some code works, and it's very powerful, although it's not the most used feature of Julia, but when it's used, it's really powerful. So this brings me back to the sort of the other part that really ties all things together is that the way Julia works is that when you have a function, so a function in Julia is just a name. So for example, plus, so the plus operator is just a function, but then a function has many methods. And a method is just a combination of the function plus the type of its arguments. So for example, I have the plus operators and I ask Julia for the methods it has. And it shows me a list of a bunch of different methods. For example, I have plus bool, which is simply the addition of two Boolean numbers. Or down there, I have the addition of two so 16-bit floating point numbers. So really, you have to take the distinction between your function, which is just a name, and the methods, which are the actual implementations of your function for a specific combination of types. And the other important part is that, okay, because I said Julia is JIT compiled, this entails that when you call a function for the first time, it looks at the function and it looks at the types you called it with. And if it has not found, so if you have not called that function with these types yet, it will compile a specialized version of your function specifically for that type combination, and then keep it in memory. So the first time you call your function with new types, it's a bit slow because it has to compile it. But then afterwards, it has the compiled version to use and it reuses it, and so your code is much faster. But so yeah, this is the end of my slides, but then I move on to a notebook to illustrate directly what I'm talking about. So really, if someone asks you what's the secret sauce behind Julia's piece, that is both the type system, it's a combination of all three things. So you have the JIT compiling that plays into the type system that plays the multiple dispatch. But I think this will be better explained with a notebook. Now, if anyone has questions, again, feel free to ask them. Otherwise, I will move straight on. So tell me if I'm going too fast because I feel like I've been going very fast through my slides. But anyway, so I have this first notebook to show you what you can do with multiple dispatch. So for example, here, note by the way, this is a Jupyter notebook which we can run on VS Codium. As a side note, so VS Code has a really nice extension for Julia. So if you're trying to use Julia, I would recommend using VS Code to do that with this the official Julia extension because it makes your life much easier. But anyway, so let's go back to the notebook. So yeah, in this notebook, I'll illustrate two examples of multiple dispatch. So the first one is to start define a function. So we have this function f of x. So this is one of the ways you can define a function within a single line. So I define my function f of x equal 2x squared plus x, and I can run it. And you can see it takes some time to compile because it has to launch the Julia kernel. And it says, okay, this is a generic function with one method. So this means generic means, okay, I have not specified any types here. So it assumes that it can take any type and it will try and run it. So now if I can call it with an integer. So 1 is just an integer literal. And I can call it and get 3 as we expect. And then if I call it with 1.0, which is for a floating point, then I get 3.0 as a floating point number. So indeed, you see that when we call our functions with different types, we get different types out. And when you're trying to debug your code, it's nice to use a couple of macros. So one of the nice ones is this one called code LLVM, which shows you actually for a given call, what is the generated code that the compiler provides for that function call. So for example, if I call my function on a floating point argument, you can see that it runs and I get essentially a function that's 3 instructions. So that's another thing to note that because these are three very simple instructions, this function will be very fast. Whereas if I instead force my type to be any, it will be a bit slower. Apparently not. Okay. never mind. I'll show you instead what happens when I call it with 1. So you see, if I call it with an integer, it starts using actual integer operations. So this shows you that the compiler really does specialize your function for the types of your arguments. Yeah, you can find other macros like this that tell you useful information about your function. So, okay, this is so far so good, but let's consider now this function that's simply 2x squared plus x divided by 2. And okay, I can still call it with a floating point argument and it works. Now, if I call it on an integer, I have a problem. It also returns a floating point. So what happened? Well, the problem is that in my function here, I use the division operator slash, which in Julia is just the exact division. So when you compute the exact division of two integers in Julia, you get a floating point number. If you wanted the integer division, you needed to use another function called div. And I can actually solve my problem here. Say I wanted to have that when I call my function g on integers, it should always return an integer. Then I can just redefine what it means for my function. I can redefine my function when I call it with an integer argument. So example, notice here, I put a type annotation, say, okay, g when n is of type int is this expression. So now if I re-evaluate g on an integer, I get an integer as I wanted. So, and notice that this has not changed the behavior of my function for floating point numbers. So really, when you do this, I'm overloading what my function does for different types. So this means that you can define a function for different types and it won't interfere with each other. Now, so far so good, but we still have the problem if I call my function again, but on an 32-bit integer. So int is a shorthand for int64, so the 64-bit integer, and int32 is the 32-bit integer. And if I call it that on a 32-bit integer, I still get a floating point number. So, okay, maybe we have to fix this by defining a new method for int32, but then we'll also have to do that for every other integer types. And then if someone else brings in another integer type, they'll have to define new methods for that as well. But actually, we don't have to do any of that because remember, we have these abstract types and that's where they come in. So in Julia, we have the integer type, which is the abstract type for all integers. And so I can define my function g for any integer types, which is the same as before. Now, if I call g on a 32-bit integer, I still get an integer. So this gives you a small taste of what you can do with multiple dispatch, is that you can really define your function and then refine it if you have either a different behavior you expect for different types, or even if you have a better implementation. So for instance, if you're doing linear algebra, the sort of standard Julia library has a types for so normal matrices, but then triangular and symmetric matrices. And so for all of these different types of matrices, you have efficient algorithm for computing a matrix product, a linear solve, and using linear dispatch, you can do exactly this very fast. So because you have to say, oh, I want my matrix multiplication for when one of my matrices is a diagonal or a triangular to be this, and otherwise just that, and it works. So, okay, still no question. So I'll move on to the next bit. So to give you a more advanced example of what you can do with multiple dispatch. So note that this is taken from an example from one of the creators of Julia about so automatic differentiation, but we'll go through it. So we'll start by defining a new type called dual, which is will be a subtype of number, and it will have just two fields, so x and y, both of type float64. And you have some description of math. You can think of this either as something that looks like a complex numbers, but where the imaginary part has squared to 0. But another way to interpret this is that x is the value of some function evaluated at a point, and y is simply the derivative of that function at the same point. And in the next it's about 10 lines, I'm going to define what it's, because dual is a subtype of number, I will define what it means to add, subtract, multiply, and divide these dual numbers, and then how they work when they meet real numbers. So for example, if you look at the first two examples here, I define it what my plus operator and what my minus operator means for two dual numbers, and it's, as you would expect, a dot x plus b dot x and a dot y plus b dot y, same for minus. But then for the multiply and divide operations, okay, for the multiply is the same and the divide is the same, but then here we have something that, if you squint a bit, it's actually the rule for the derivative of a product, right? Because you have, if a dot y is the derivative of y, you have a dot y prime times b dot x plus a dot x times the derivative of b. And it's exactly the same thing for the divide operator. Then on the bottom, I have some rules that tell me, okay, how to convert a real number to a dual number. If I'm trying to add a real number and and some other number, then it should be a dual number. Note here that I'm having again this type dual, so I'm dispatching on the type. So I mentioned that you can work with types directly. So this is an example. Then on the bottom is just, okay, how to print a dual number in the when I have it in the REPL. So if I run this, okay, it works. And we can try our new type on the function. So let's keep using our function f that we defined previously. So I define it on integer, on a float, and then on a dual, and we see, okay, we have an integer, a float, and then essentially a dual number. So we have 3, so just the function applied on x, and then the derivative of f applied on x. And you can check that this is indeed the derivative of your function f of x at 1. So if you look at how we define f of x, so we define that as 2x squared plus x. So the derivative that would be 4x plus 1. So indeed, when you call it at 1, we get 5. But let's try a more complicated example. So the function here is an implementation of the Babylonian method for computing the square root of a number. So it's a fairly simple iterative method, but you'll see that I'm starting. It's Newton's method applied to the square root. And so you start out with some function and x here some initial guess, and you just do a couple of iterations to refine your guess to the proper square root. And I can call it on some just regular old floating point numbers and see if it's correct. So notice that here I have pi. So I mentioned that you can use Unicode. So pi here is just a shorthand for the number pi. And then next one is you have the square root symbol, which again will be a shorthand for the square root function. You can also just use sqrt parentheses and it'll do the same. So it does look like indeed my Babylonian function does compute the square root of pi and then the square root of 2 pretty accurately. Okay, now what happens when I call Babylonian on a dual? Well, actually it just works. This might be surprising because we haven't done anything to tell it about dual numbers, but because I've defined what it means to add and do arithmetic on my dual numbers, because this function here only involves arithmetic operations, it works. And so with a single call of Babylonian on my dual number, I get the value of the square root of 2, and I also get the derivative of the square roots evaluated too. And we can compare it to the actual analytical expression that this is indeed correct. So just to bring in the point that in just about 10 lines here, we've defined a very simple implementation of something called automatic differentiation, because I'm automatically computing the derivative of a function in a way that is not finite differences and it's not symbolic manipulation. It's completely different. And the way we've defined it, it will work with almost all numerical functions. We might need to define some additional primitives here and there, but pretty much any numerical Julia function I define, this will work. And if you try to do this in Python while keeping it fast, it's impossible. You need to either define your own functions or define your own types, and it won't work with anything from NumPy, because then NumPy underneath will use stuff from so C code or Fortran code, and so you cannot apply these types to that. And similarly, if you want to do that in C, C++, or Fortran, again, you'd also have to either rewrite the entire math library to support your new types, or you have to write a special compiler. And so in Julia, it's very easy because of the way the language is defined, and it's still fast. And if you wanted to do in either Python or C Fortran, it will be a lot of work. So I hope this has convinced you that multiple dispatch is somewhat powerful. Okay, great. I see one question. So is it possible to perform symbolic calculations with Julia? Yes, there is. So Julia has a package called Symbolics, which actually has grown out of differential equations. So they wanted to be able to specify dynamical systems symbolically, and so they defined. They created this package for symbolic computation, and it's giving a run for it's giving SymPy a run for money. So for the other questions, so a dual number, you don't really have to worry too much about it. It's just you can think of this as a number of this form. So it looks like a complex number with x and y, but epsilon here is kind of like the imaginary unit I, except it satisfies e squared, epsilon squared equals 0. And so you can define it as that, and this is actually fairly old. I think it goes back to Clifford algebras. But you can also think of this as the algebra of x being just a function evaluated as points, and y being the derivative of that function evaluated at the same point. So you can check that with this definition, you get the rules as described here. Okay, any other questions? I've been told that one should wait about 6 seconds for people to ask questions, so maybe I should try that. Okay, otherwise, we'll move on to the next part. So can someone tell me how much time I have left? So I think I might have up until 12:40, is that correct? I'll start the next part until waiting for a response. So moving on to the next part. One thing that's pretty important, especially for numerical computing, is that you want to be able to benchmark your code. You want to be able to tell, I have my code, is it performant? How well does it run? Which parts are slow and I should optimize? And so one of the basic tools in that is to simply benchmark the code, run it a bunch of times and measure how fast it runs. So again, I've taken a lot of this from a very excellent blog post that I encourage you to read on your own time. So note that if you want to follow this, you'll have to run this cell that adds a couple of packages to your Julia installation if you haven't installed Julia. But otherwise, you can start straight to the example. So for example, we simply be examining the performance of matrix multiplication. So here I have a very naive implementation of a function that takes three matrices, C, A, and B, and computes the product C equals AB, or at least it updates, so it computes C equals C plus the product A and B, and it does it without allocating any memory. So you can sort of recognize that we have 3 loops. As a comment also, note that I only have a single loop for my 3 indices. So that's one nice sort of syntactic rule in Julia. You can sort of fuse loops like this, so you don't have to both your first loop and then indent next loop, indent next loop. So it sort of makes your code a bit more readable. And so if you look at this, it's pretty much what you do expect from matrix multiplication, right? I'm copying Cij is the sum of Aik times Bkg. Okay, and I can run it. I need to select the kernel, so yeah, this one. now it's decided to run. So again, you see that anytime we restart Julia, it can take a couple of seconds to get it started. So we'll measure the performance of our simple multiplication with some matrix. So I define n to be 256, and I define my three matrices to being simply random numbers of size n. So A, B, A, C are all three matrices of size n. And one very simple macro you can use from the standard libraries, the time macro, which simply you slap it in front of a function call, and it tells you how much time it takes to evaluate. So if I run my simple build time, you can see that it took about maybe not a half, but still some fraction of a second. But you also see the message here that tells, oh, it needed to do 30,000 allocations to allocate about a megabyte of memory. It tells you that about 50, it spent about this much time for compiling. So this is what I mentioned because it did compile. This is the first time I've called this function, so it has to compile it first. And so it took some time, but now if I run it again, you can see that now it's about twice as fast. So really the compilation time is only important for the first time you call your function. Okay, so time is good, but we'll need some more proper tools to really benchmark our function. So to that, we have the very nice package called benchmark tools, which provides a bunch macros including btime and benchmark. And so, for example, I can call the benchmark macro, which will run my function or my function call multiple times and then return me some description of some statistics of the time it measured. So if you run it again, you can see it takes a couple of seconds. This is slower than I remember. It was faster when I tried it. Okay, so you can see now that we have some histogram that tells us, okay, the minimum was about 22 milliseconds, the maximum was 40 milliseconds, and the median is about 30. So interesting because it was much faster. It was about 20 milliseconds for when I tried it earlier. So, but yeah, you can see that we have a histogram of the times it took to run our function. We also have an estimate of the memory it uses. So here, because this function does not allocate any memory, we have no needed allocations. So one thing to keep in mind, allocations slow down your code. So if you want performance, you have to avoid it as much as possible. But okay, let's compare with the equivalent function from the standard library. So if you look at linear algebra, which is the part of the standard library that does anything for, as you might have guessed, linear algebra, and it defines this function mul that is exactly the same as the function we defined. So I can run it and I can, again, take a benchmark of it. And again, it has to compile it. So I'm guessing it has to recompile a bunch of things. Okay, now we see that it's much faster than our implementation because the median is about 2 milliseconds, so it's about more than 20 times faster than maybe 10 times faster anyway. So it's much faster than our function above and across all metrics. And the next part of this is also to show you a couple of very simple optimizations that you can apply to our base function to get closer to the standard library. So one thing, a first very simple thing is that because Julia has arrays and it's the main data structure, you have to worry about what's the storage order of your array. So in Julia, as in Python, as in Fortran, the arrays are stored in row major order. So which means if you have a matrix, the matrix is stored in memory by column. So I'm telling, okay, I've got it wrong. It's not row, it's column major. So something. So in Julia, the arrays are stored in column major order, which means if you have a matrix, The matrix in memory is stored by columns. We have first column, then the next column, then the next column, and so on. And so because of the way that modern processors work, it's best to access memory in a contiguous manner. So you don't want to be making big jumps. And so that means that it's faster to access a matrix by column rather than by line. And so if we change the order of our loops here so that aik here, we evaluate it first. So we stick by k, so we take the kth column and then we access it, just the kth, so the successive element of the kth column of A. Unfortunately, we cannot do the same for J, for B. This will be already a simple improvement. So we can benchmark it a little bit and see that after a couple of seconds, we'll see that it is in fact somewhat faster. There we go. So we saw that compared to our, here we had about 30 milliseconds and we've moved from 30 to about 20 milliseconds. So, okay, pretty nice, but was still very far from the standard library. So let's try another trick. So anytime you access an array in Julia, it performs a bounce check. So it checks that the indices you're calling are in fact valid indices for your array, that you're not trying to access memory outside of your array. But if you know that the index is correct, that it is in fact within the bounds of your array, you can get a little more performance just by using the macro inbounds. So when you slap inbounds in front of an expression, you'll simply tell Julia, okay, don't bother checking the bounds in index and operations in this. So here I have the same order of the loops as the previous function, but I've only stuck the inbounds macro to tell it that, okay, here do not check that the indices are inbounds. And we'll see that just that will have a pretty nice impact on our performance. But as I mentioned, we can still do a bit better. So yeah, we moved from about 20 milliseconds to 3 milliseconds. So almost 10 times improvement. So pretty not bad for just a single macro call that's in the standard library. Now, the next thing we might try is to actually use some either distributed or multi-threading. Unfortunately, I cannot show that directly in the notebook because I cannot start a notebook with multiple threads, but we can do that easily by looking at the. So if you want to start Julia multiple threads, you call Julia -- threads, and then you type the number of threads. So here I'll start Julia with 4 threads. And now if I copy this function here, there we go, I can copy it. So I now have my function. And then I will copy these 3 lines of code to run my benchmark. So it defined my 3 arrays and imported the benchmark package and then completing the benchmark. And after some time, we should see that it did in fact use my 4 threads. So yeah, you see that using multi-threaded, and notice also that to have my code run on multi-threaded, I only had to add a single macro in front of my for loop. So all I had to do is to sort of first isolate my first loop and then call threads.threads. And so this just tells, take this loop and run it in multi-threaded mode. And we see that indeed it did have a nice impact on our performance. We're down to 1.4 milliseconds. So we're actually getting very close to the standard library, although the standard library does not use multi-threading. So we maybe not do that in the future. But one downside is that to use multi-threading, you have to allocate some things. So we see that here it allocated about 2 kilobytes and for 20 allocations. So keep that in mind. Anyway, so and here you can see the old result for my function the same, but without the multi-threading, it's essentially the same as if I was doing this. Okay, so I have one last trick to show you is that you have some really nice packages in Julia to just get performance for free. And so one of those is called loop vectorization. And it's a package that exports in particular one macro called turbo, which again, you can just slap in front of your loop and it will perform some magic to make your operating instruction. So it's a single processor directive can be vectorized at the level of the processor, and so those are called single instruction multiple data. And Julia can actually make use of that. So I can define my function turbo using this new so using in part this this macro, and I can benchmark it. And normally we should be slightly faster than the standard library. And all of that with just a single macro call that we had to add in front of our loop. So as you can see, it's pretty easy and pretty nice to get some almost free performance lunch in Julia. So is it possible to combine Turbo and multi-threading? Probably, though I think you might be able to say run the first loop in multi-threads and then the next ones in using Turbo. That might be possible, but Turbo in particular is already pretty fast. So yeah, we see that now with Turbo we're actually under 1 millisecond, so pretty much almost faster than the standard library. So we have a question about, is the matrix multiplication function methods in the standard library implemented in Julia, or does it use BLAS? So it does use BLAS for the matmos. I do believe so. Note that that's one really nice thing is that actually the actual BLAS that Julia uses, you can change that at runtime. So if you have different version of BLAS, there's a package that lets you decide at runtime which version of BLAS you're using. So it's nice because the BLAS you're using is actually whichever you want, and you can decide at runtime. But I think it might not be impossible to see that to see a BLAS purely implemented in Julia, because as you can see, you can get some pretty decent performance. So yeah, notice that here with just a couple of macros, we can be pretty much as fast as the standard library. But keep in mind that we're only looking at matrices of size through 56, and my implementation here does not check all the things that I should. So here I suspect it might easily find some errors that you would not have in the standard library. Okay, so I'll wrap up by simply showing you a nice plot of all our results. So because okay, but when I run the benchmark macro, it does not simply show me something, it actually returns me an object with some data. So that's why I've always been assigning to a variable. So I can in particular look at my benchmark objects .times, which is simply all the times it measured. And so I can then look at boxplot for that. So, yeah. Again, we see another nice example of, I need to run my threaded example again, but on the notebook. Sorry about that. There we go. And yeah, this should take about the same time as this. So we'll wait a couple seconds. Yeah, notice that we keep seeing these packages taking some time to load. So also for packages, when you load a new package for the first time, it have to precompile some things. But then the next times you load that package, some of the things will already be precompiled. So do keep in mind that it is one issue anytime you use Julia, and if you rerun your program, you will have to recompile a few things. And so one of the impacts I suspect for that is that if you're trying to run Julia on the cluster, you might be prefer running fewer large jobs rather than many small ones. So now if I can actually get my plot, so here we have the data for the different functions. So we can see that the base model actually has quite a lot of variance, right? It's mostly the fastest, but we see that the box was pretty wide and it has quite a few outliers. And yeah, we see otherwise we see that our simple algorithm was pretty bad, and then when we changed the order of the loops, we had some improvement. Then inbounds was even better, and then the threaded version was somewhat better, but then we see that the turbo really did some amazing work there. So yeah, as you can see, benchmarking code in Julia is very easy. I have not shown how to profile your Julia code, so it's another thing you can do, and you have a couple of packages for that, and it's just about as easy as you'd expect. You just run a macro, or yeah, you run a macro to profile your function call, and then you get the data that you can show and examine on your browser for that. Okay, are there any other questions for now? Let me grab a drink. Okay, no questions, so I'll move on to the last part about some basic parallel computing. So we've already seen how to do some simple multi-threaded, and here I'll show how to do distributed. So multi-threaded is one thing, and another thing you can do is actually run on multiple cores, and this is especially relevant if you're trying to run Julia on the clusters. And so I'll show a first example of using a couple packages. So again, you might have to install some packages, especially folds and transducers. Okay, it seems to have completely forgotten that I've run these notebooks before, so it has to redo all the things. That's very annoying, so it's slower than it should be. But anyway, so I'm loading these three packages. Note that distributed is from the standard library. It's just the package for running your code on multiple processors, and it had function at prox that I can run to simply get more processes or get more processors at runtime. So here I'm calling add proc4 to tell me, okay, give me 4 cores to run my code on. And as a very first example, no, the only example for this notebook is we'll simply try, okay, I want to find the number of palindromic primes under 210 to the 8. So to remember, a prime number is simply an integer that is only dividable by 1 or itself, and a number is palindromic if you write it in decimal and then flip the decimals, it's the same number. And so we'll actually define a couple of functions for that. So the first one is prime, and it's simply a function that takes an integer and tells me whether it is prime or not. And note here that I've added the everywhere macro, which simply tells the Julia compiler to make that function available to all the cores. So because I want to be able to run that function on all my different cores, I need to add the everywhere macro to make sure that all the cores are aware that there is this function that exists. Then the same thing for palindromic. So for palindromic, I'm simply calling the digits function, which takes an integer and returns a list of the digits in decimal here. And then to check if it's palindromic, I simply check if the array of digits is the same as the reverse of its array. So reverse simply changes the order. And let's take 10 to the 8. And the next few lines show two different ways of computing the what we want. So one used the false.sum functionally from some users, and note here that it has to be read from left to right. So because This here is the pipe operator, so it takes an argument and gives it to the function on the right. So I started with the numbers from 1 to n, and then I want to apply a filter. So filter just tells me only keep the ones that are prime. So I filter on is prime, so it applies the is prime function, and if it's true, it will keep the number, otherwise it will throw it away. And then it passes to a filter is palindromic. So first I'm looking, is it a prime number, and then is it palindromic? And then to get the count, I simply map each n to 1, and then I take the sum of these. And I can run this, and now this will take a minute because by default, all of this will run in multi-threaded. But because my notebook only has a single thread, it has to run on a single core. So it will take a minute to run, but we'll get the result eventually. And then the next line here will use a function from this transducers, which does run by default in distributed. So once we get the result of that, we'll be able to run it. Yeah, I see. I seem to be running slightly faster than I intended. So luckily, I have one last example of actually how to run Julia distributed job on the cluster. So stay tuned. Yeah, so you see that this takes a while, but this was fairly easy to write, right? I only want to express that I have my numbers from 1 to n. I only want to keep the ones that are prime. I only want to keep the ones that are palindromic, and then take the sum of something of that. So I think in about a couple of seconds it should be done. Somehow everything seems to run slower right now, even though an hour ago it was about 1 minute 30. So the joys of live demoing. I see another question. Excellent. So yes, the distributed package is usable for multi-node parallelism, I do believe. And in fact, there is a package called shared arrays or distributed arrays, which allows you to have an array, but that is spread over multiple nodes. But it still acts like an array. Okay, so in the meantime, my code has finished, so it took about 2 minutes to run it in single threaded. And it found that, okay, there are 782 palindromic prime numbers under 10 to the 8th. And if I run the next cell, which again, this runs in distributed mode, and wrote that, okay, it's essentially to map the first set to the last one. Fold xd is about the last part, and so I'm folding the plus operator, so I'm taking a sum. And then the rest is simply an expression that tells me, okay, over this collection, and then only if it's prime and if it's palindromic. And this all gets interpreted into a distributed program that spits out the answer. Yeah, to give you some other indications on so running Julia in distributed, there are a couple packages, for example, for running Julia with MPI. So I think just about any paradigm to do distributed processing you have in Julia, so you have MPI.gl. Another package which unfortunately does not work on the clusters here. So there is a package called clusters managers, which allows you to, in principle, directly interface with Slurm. But unfortunately, you need to have srun to be able to run srun. So it does not work for sbatch. So, okay, so we see that the function here is finished in slightly faster in 1 minute. So I think because it had to compile, it was pretty slow. But yeah, we found the same answer in this. All of this run in the distributed. So as a last example, so I will show you how to run Julia on the cluster. So I have a very simple example that will not take long. So connect to the Hercules. So I kindly asked the administrators at the Hercule cluster to add Julia to the available modules, so we can the MLAV Julia. It should eventually tell me that there are two modules. So you have Julia 1.6.7, the long-term support version, and then the latest version 1.8.2. So we load 1.8.2 Julia. So now I can call Julia, but before that, I have a small example. So I have a couple of Julia files here, and in particular, we can look at the distributed.jl. It is a very simple Julia program which only uses distributed. So the way it works is that I'm first using distributed, and again, I'm adding 4 processes, and then I'm telling me, okay, tell me what the number of processes is, tell me what the number of work is, and then I have this loop that sends instructions to each worker. So here I'm doing something very simple. I'm saying get the ID, PID, and host of each worker and print them. Then afterwards, you have to remove them. Then, because this is on Slurm, you need to write a Slurm job. So look at the batch job. So this is a Slurm batch file, as you know and love. So I'm running on the batch partition. The name is Julia test. The output is res. I'm running on a single node and giving it 4 CPUs with 1 gigabyte. I can now close, and if I want, I can try and demonstrate it live. Hopefully it will work. So see that it has been running. So because it's a very small job, it found it's able to run. So and you can see it takes some time because even though it's simpler, it has to start and recompile a bunch of things. So normally it takes about 30 seconds to run. So it's running, and now it's done. So we can look at the results. So because we told it to output in rest.txt, then we have the result of our program. So it told us we have 5 processes and 4 workers, and it told us so again the ID, PID, and the host name of our workers. So this is very bare bones, but I think you can see how you can use this to run your Julia programs on the cluster. Okay, with that, I'm done 15 minutes too early. So if you have questions, feel free to ask. Otherwise, we'll all be very bored until lunchtime. As a side note, you can still look at all the resources. So all the code I've shown here and the notebooks are in this web page, and I've also put a lot of links to packages or stuff in Julia that might be interesting. For example, if you're working in chemistry or in physics, there are a bunch of packages useful for that. Okay, so do I have a good reference book to recommend? So as far as proper books go, not necessarily. If you want to learn Julia, I'd say the Julia manual is pretty good. One nice book that I read was Design Patterns in Julia by I forgot the name, but it was one nice book, but it was more about design patterns. But I know there have been a couple of um, I've seen a couple of books recently about different parts. So, for example, I know there's a book about data science in Julia that does covers that, and maybe, yeah, that's one thing that's missing is that there are not yet quite so many good books. Although I think there's at least one book for like running Julia in parallel on the clusters, but so far it's still there's not that much stuff. Any other questions? So is there an equivalent to RStudio for R but for Julia? So I guess the equivalent would be VS Code. So there used to be something called Juno, which was essentially a modified version of Atom that had some special packages for Julia, but then since then Atom is dead. So nowadays the sort of best experience you can get for running Julia is probably using VS Code with the Julia extension. Okay, so for the next question, why isn't Julia more popular if it's both user friendly and fast? So it's a bit of a trick question because it is indeed both user friendly and fast, but I think until very recently, one argument you could have is that the ecosystem is not developed enough. So there are not enough packages, it's brittle, there's not enough documentation, and that's still true to some extent. So it's definitely a language that it's easy, it's nice if you're a bit of a power user, but then you might go into Julia and say, this thing that I used to do in Python or R, I do not have in Julia, it sucks, so I'm going back to my own language. One note is that if you're trying to move to Julia, you do not have to throw your old code away. So for example, by default in Julia, you can call C and Fortran functions from the standard library. So if you have an old Fortran library that's compiled, you can still run the functions from that. Same for Python. So there's a really nice package called PyCo that lets you pretty much import any Python packages and use it within Julia. So it's pretty nice. But for the user-friendly, really, I think it's a bit of a question, a problem of critical mass. Because first, you did not, as I mentioned, the Julia community is very small. So compared to Python, it's tiny, absolutely tiny. And so for many people, it is not simply having a nice, user-friendly, and fast language is not enough to justify learning an entire new language. So I think this might be one of the biggest reasons. Yeah, so to come back to the question about notebooks, so yeah, I've used notebooks here to demonstrate the code. There's in fact, so this is a Jupyter notebook. Fun fact: the Ju in Jupyter is actually for Julia, so it's actually not all for Python. So technically, it's Julia, Python, and R, but people are usually surprised when you tell them that. But there's actually a pure Julia notebook system called Pluto. It's pretty nice, although I haven't used it for presenting for other reasons.